Hello.
Yes,
You
sir.
are able to
It's, yes, sir. We can hear you. You can see the presentations. Okay. So it's 6 and our capacity is full. We have 500 plus participants.
Yeah.
Okay, so good evening, everyone. On behalf of Departments of Microbiology and Biotechnology of AC College, I welcome you all to this session on chromatography, types and its recent applications by Dr. Ajit Datar that we have organized under the aegis of STAR DBT status. I request Rajita to kindly introduce our speaker for the day and continue with the session. Thank you.
Good evening, everyone. We are fortunate to have with us Dr. Ajit Datar, who is currently working as an advisor to Shimadzu Analytical India Private Limited, Mumbai, in the Customer Support Center. His main job profile is to provide instrumental analysis support to customers. Prior to Shimadzu, he was with Thermoelectron and served this organization as general manager. He was responsible for promoting advanced mass spectrometry products of thermophenigen in India. He served for Chromeline and IR Technology as a technical director and senior manager for a period of 15 years. Before that, he was also his first assignment was with Central Research Station of Associated Cement Limited as research officer. He served there for another 12 years. He has developed several methods for characterization of catalyst and process products using catalyst. He indigenously developed bed surface area analyzer and particle size analyzer. Dr. Datar finished his MSc in 1971 and PhD in 1976 from the Analytical Chemistry Division of BRC. He is currently working as adjunct professor in Khalsa College and a visiting faculty in several other colleges in Mumbai. He has several publications to his name and is also a guide for PhD in Mumbai University. Thank you, sir, for accepting our invitation. We now welcome you to start with the lecture.
Thank you, ma'am, for your kind words. And let me begin my presentation on chromatography. Oh, I'm sorry, it is chromatography. So we are engrossed with that word so much that instead of talking about chromatography, I said it is chromatography. Okay. But now here onwards, I will definitely talk the correct way. Okay, chromatography is one of the analytical techniques which is very popular in industry, especially pharmaceutical industry. And they use chromatography day in and day out for quality control, for research, for method developments for their products. So it is being used enormously in pharmaceutical industry, and it is an analytical tool. It is used for biological sciences also. It is used for chemical sciences also. And for that purpose, I'm going to talk about this particular technique with respect to both biological sciences as well as chemical sciences. And as I said, it is an analytical instrument. I would like to introduce first some concepts of analytical chemistry to the chromatography by itself. Okay, so I would like to introduce to you an analytical chemist. And the analytical chemist is what happened. Moving. Yeah. Okay, so what you're seeing is an analytical chemist. He is a juggler. He's playing with some objects, and those objects are sensitivity, selectivity, separation, structure, and speed. These are 5 components of analytical chemistry. Because without that, the analytical chemist cannot work. I mean, he always talks about sensitivity, how sensitive his analytical tool is, how low he can determine a particular analyte in his given sample, whether the instrument is to detect that particular analyte in sample or not. So sensitivity is very important, and the instruments are becoming more and more sensitive. We are not talking about percentage. We do not talk about ppm now. We talk about ppb or ppt or something like that. So we go down and down as far as the detection levels are concerned. So sensitivity is very important. Selectivity is also equally important, because we have to determine a given analyte very selectively in a very complex matrix. To give you an example, if I want to measure a particular drug concentration in the blood plasma, you know how complex is blood plasma, and in that you have to determine a very small quantity, parts per billion level of analyte. Your method has to be very selective. It should be able to selectively measure that analyte. Then of course you have to carry out some kind of a separation before you do any analysis, and this separation could be simple things like filtration, centrifugation, liquid extraction. It could be solid phase extraction, and of course the best technique for separation is chromatography, which I'm going to talk to you about. Then many times also is very critical. Many times organic molecule has to be, you to find out what is the structure of that organic molecule. It could be any molecule. It could be a drug molecule. It could be a peptide. It could be protein, saccharide. It could be any organic molecule for which you need to find out the structure of that molecule. And that is a qualitative part. So we do a lot of qualitative analysis in addition to what is the quantitative analysis. Then we need to have a speed of analysis. You can't take a lot of time for the analysis, especially in industry. You cannot delay your analysis. So speed of analysis is very important. Then if you want to manage to play with this 5S, you have to do something to suppress some of the errors. So sampling error needs to be suppressed. How you that is very, very important. Have you done the sample preparation properly or not? Because sampling error involves two things: the uh, choosing the correct sample and representative sample, as well as how you prepare your sample. If you have to do some liquid extraction, have you completed your extraction properly or not? So sampling error can happen because of all these factors, and you have to take care of that. So you have to reduce those kind of errors. There is always a background associated with your analysis. A background can come because of the matrix. When you want to analyze something in plasma, or if you want to analyze something in food, the pesticide in food, you require to reduce the background. Otherwise, that background signal will be so much that it will not allow you to measure your analyte. So background needs to be reduced. And there is always some kind of a noise associated with any electronic equipment, and that noise also has to be reduced. So when we actually measure sensitivity, we always talk about signal to noise ratio, and any specification of any analytical tool always describes this number. What is the signal to noise ratio for a given concentration? So signal to noise ratio is very, very critical. And for that, unless and until we have low noise, we cannot have signal to noise ratio higher. So one way of getting good signal to noise ratio is to reduce the noise level. So if you want to be a good analytical chemist, you need to know all these factors. And today, analytical chemistry is such a field that it encompasses everything. It is part of chemistry, it is part of biology. A lot of biological research work depends on a lot of analytical chemistry. And that is why the understanding of chromatography and spectroscopy, these two techniques is must for all the biological students, especially those who are doing research in the field of biology. Okay, so that is why I just wanted to introduce to you these concepts, because many of you have a very little background probably of analytical chemistry. So I thought of giving this information to you. Yes, so we know that there are a number of diverse methods for separation. I have listed some of them in my next slide. So there are a lot of methods for separation. Of course, the best method for separation is chromatography. As I said many times, a sample preparation by itself, you require to do some kind of a separation. It could be, as I said, filtration. If sample has some undissolved particles in that, so you have to remove them by filtration. So are very, very large in numbers. I listed some of them, but the best method for separation, of course, is chromatography, about which we are going to talk about. So what is the beginning of chromatography? I think many of you have learned some aspects of chromatography. This person very well, Mikhail Sweat, who has developed this in 1903. And he was a Russian botanist, and he did some work by which he separated the plant pigments, especially the chlorophyll, and by using chromatic method. Of course, he named his method chromatography because he could get, let us see what he did, and then we will understand why he named this technique as chromatography. Chroma means color, graphene means writing, and what he did, if we understand, then we'll know why he gave that name. Well, before that, these are the milestones in chromatography. So 1903, Mikhail Sweat was the beginner of this particular technique. Then 1931, Lederer and Kuhn did some work on carotenoids. Sales and exchange was developed. River phase chromatography was developed in 1950. 1952, James and Martin developed gas chromatography. 1954, the first Nobel Prize in chromatography was obtained by Martin and Sage. Gel permeation technique was developed in 1959, and the first ELS instrument came into existence in 1965. There are, in just small period, when the real development of chromatography happened between 37 and 72, 12 Nobel Prizes were awarded on this particular subject, chromatography. So you can imagine the importance of this technique. The scientists during that time felt this technique is very important, and that is why so many Nobel Prizes were awarded in such a short time. Well, these are the this is the experiment which Sweat did. He had a chlorophyll mixture which he put onto a column. This column was consisting of this calcium carbonate powder, a chalk powder, and that was put in a petrol ether, and he put the solution, petroleum ether actually, on the top of it, and then the chlorophyll was added, and then the components of chlorophyll got separated. At that time, there was a thought that chlorophyll is a single compound. So some people were thinking that chlorophyll is a single compound. Some people were thinking that chlorophyll is a mixture of many components. So Mikhail Sweat thought of proving either side of this, and that is why he did this experiment. And when he put the chlorophyll onto the column and put the top and try to separate the bands of whatever chlorophyll was added, to his surprise, he found he got 5 bands. And then when he analyzed these 5 bands and their structures were identified, the names were given, and then he could see 5 different compounds, and he named them as they were found to be beta chlorophyll, alpha chlorophyll, xanthophyll, viola xanthine, and carotene. So these 5 compounds got separated on this particular column. The white background of the column, because of the chalk and the green and yellowish green and dark green colors of these compounds, it was looking like on the white background, he was able to see those color being written on the white background. And that is why he named this technique as chromatography. Today, of course, we don't separate the components which are only colored. We separate all different types of compounds which are even non-colored. And the name, of course, what is given by Mikhail Sweat still continues. These are the structures of all those compounds you can see here. This is one compound, a lot of hydrocarbon tail. This is xanthophyll, beta chlorophyll was over, viola xanthine, carotene. So all those 5 compounds are given a structure, and as a chemist and as a researcher, we know that these compounds got separated. But 2 questions can come to our mind: the why we got this separation. And these 2 questions are: why these 5 solutes separate on the column? What was the reason for their separation? And that we have to find out. And 2, how do these 5 solutes separate on the column? So we have to answer these 2 questions to make us clear about what this technique does. And then let us try to find out the answer. The 5 solutes have different migration velocities across the column of calcium carbonate. So one was moving faster, one was slower. That is why they got separated, and one was still slower and one was still slower. And that is how the separation of all the 5 components happened, because they have different migration velocities. Then We answered one question, but the second question, why one has more retention on the column, why one was moving faster on the column. So what must be the reason for that? So the reason could be because the calcium carbonate is an adsorbent. We can say that they have different degrees of adsorption on the surface of calcium carbonate. That is why one was retained on the column longer time and the other was retained for the shorter time, and that is how they moved on the column and got separated. Then of course there could be one more reason. The property of analyte also could be responsible for its adsorption on column. So there could be three factors which are responsible for separation. And then if we do the phenomena of separation was adsorption, we can call this technique as column adsorption chromatography. Let us imagine this as a race happening. So there are 5 players who started from one particular line and now they are moving fast, and we find that they are getting separated. So the migration velocities being different, their velocities being different, they could get separated. So that is one reason which we could say. We are quite familiar with the phenomena of adsorption. It is a surface phenomena in which some solutes, which are called as adsorbates, absorb the surface of another solute, which we call an adsorbent. So the column material, which we call as the chalk powder, is an adsorbent, and the chlorophyll components were called as adsorbates. So adsorption process depends on several factors. One is the surface area, and surface area depends upon the particle size. So smaller the particle size, more is the surface area, and more would be the interaction of the analyte with the surface. So particle size plays a very important role in chromatography. Another factor is porosity. So there are pores on the surface of adsorbent. If there are more number of pores, there is more surface area, and there will be more adsorption on the surface. So these factors play a role. So one part is over. Why we have a separation on an adsorbent? Now there is this article which has written by Martin and Singe, who got the Nobel Prize for this particular work in 1954. They talked about a different way of working. They thought that if adsorption can happen, and if the adsorption could be the method of separation, why can't a partition happen? So can we make a liquid stationary inside the column and put another liquid and the components passing through that liquid, which is made stationary, and can we have a separation in the column where liquid is made stationary, which is difficult, I mean, to understand how the liquid can be stationary inside the column. But they made it, and they proved that this liquid chromatography today became more popular, and that is why they got a Nobel Prize for this technique. And in this particular paper of 1941, they also recommended that, because from 1903 to 1941, everybody was using as a mobile phase. But in this paper, they recommended that the gas also can be a mobile phase. And that is how the development of gas chromatography happened after that. Okay. So this is a big article from them. I'm not going to go through that. Now, let us now look at this particular article and let us try to understand whether we can do a separation on a liquid stationary phase. Let us assume that the stationary phase in a column is liquid. If we get a separation of 3 components, I'm not talking about 5 components, say some 3 components on it by using a mobile phase, which is a different solvent than the liquid which is put, then what should be the reason for separation? I'm getting separation of 3 components. It cannot be adsorption because there is a liquid inside. It has to be partition of sample component in 2 different liquids, one which is moving and one which is stationary. It is then called as partition column chromatography. Now the question is how to make liquid stationary inside the column. Now this can happen provided we have a stationary phase which is inert. So we have some particles which are inert, which do not have any capacity to adsorb by itself. But if we can coat these particles with a liquid and then put these particles inside the column, which are coated with a liquid, the liquid coated on these particles can act as a liquid stationary phase. And by using this method, we can make a liquid stationary inside the column, and then a separation can happen because of the partitioning of the substance between two phases. One is liquid stationary phase, the liquid coated on in solid, which acts as a for separation, and the liquid which is moving through the column will be acting as a mobile phase. So we can have two methods of separation. One is liquid-liquid chromatography or liquid-liquid partition chromatography. And then we have another method which can be called as liquid-solid adsorption chromatography. So we come quickly to the definition of chromatography. This is a NIST definition. Chromatography is defined as a physical method of separation. So there is no chemistry actually involved, in which the mixture of analytes is separated using two phases. One is stationary phase and that is mobile phase, which percolates through the stationary phase. The separation occurs because of difference in affinity between the analytes and stationary phase. So there has to be some affinity of the molecules trying to separate with the stationary phase, and this affinity has to be different with respect to each other. Then only a separation can occur. So remember one thing in chromatography, that there are two phases. One is a stationary phase, other is a mobile phase. Mobile phase carries the sample along with it, and the sample components have different affinity with the stationary phase. That is how the separation occurs. So this is the way chromatography is defined, and the word affinity is very, very important. And just to make it simple to understand this particular word, if there is a marriage in a family, you get a lot of visitors, a lot of guests coming, a lot of relatives coming to your home. Those who are having very good affinity with the family in which the marriage is there, they come early, they stay for longer time after the marriage, and then they go. Then there are few who are not very close. They will come maybe one day before the marriage and may leave one day after the marriage. But those who are not having good affinity with the family, they will only come for the lunch. They have no affinity, so they will go along and they will just move out. So affinity is very important. And if the component has more affinity with the stationary phase, it will stay longer. It will not move with the mobile phase. And if the component has more affinity with the mobile phase, or it is more soluble in the mobile phase and go out, because it has more interaction with the mobile phase than the stationary phase, so it will out very fast. Okay, so let us look at the classification of chromatography. As we have said, mobile phase could be gas, and then we have gas solid chromatography as well as gas liquid chromatography. Solid chromatography means we have adsorption, we have adsorbent on which we carry out the separation of components in the mixture in the form of gases or volatiles, which can be separated by gas chromatography. And then we have liquid mobile phase, and again we can have solid, that is adsorption, like we have something like chalk or charcoal or alumina as solid adsorption, which occur. Or otherwise we have liquid partition chromatography, where the liquid is coated on inert solid, acts as a liquid in the column, and will do the separation on the basis of partition. So that is called as liquid or LLC. Then in the liquid chromatography, there are porous polymers with a particular porosity. Then the polymers which are smaller than the pores will be able to enter into the pores, and those who are larger than the pore size of the polymer, which were porous polymer, they will get out, so they will be excluded. Those who are smaller will get included in the pore, and that is why this kind of a chromatography is called as size exclusion chromatography or gel permeation chromatography. Many times we use it for analysis of large molecular weight, even biopolymers like proteins. Then we have ion exchange chromatography, where we can use ion exchange resin, and then it could be two forms. It could be cation exchange resin or it could be anion exchange resin, and then we can separate either cations or anions depending upon which resin we use. But it is in both these techniques we use liquid as a mobile phase, so this becomes a part of liquid chromatography. Then we have, instead of a column, we use a thin plate which is coated with silica, and then we carry out a separation on this thin plate, which is called as a planar chromatography, and then it is called as a TLC or thin layer chromatography, because we have a technique on where adsorbent is coated on a thin plate, and we get a separation by using that plate, by putting the component onto the plate, one side of the plate, and putting this plate into a solvent, and solvent rises up, uh, and then you get a separation. Okay, so this thin layer chromatography also is very popular, and now we have high performance thin layer chromatography also along with that. Paper chromatography also becomes a part of that, because these two techniques are called as planar chromatography, where the separation occurs on a plane of a surface. Okay, so let us look at how the separation occurs. So I have just some small video. So there are three components which are getting moved by the mobile phase. As you can say, they come out, they go to the detector, you get a first peak, second component comes out, you get a second peak, and then the third component comes out, you get a third peak. And this is called as a chromatogram. The method is called as a chromatography. Whatever you are seeing now is a chromatogram. So this chromatogram is very important because we are getting a separation of three components here, which you can see. Well, I'm just talking about how the separation occurs. As you put these sample onto the columns, let us see here, there are only two components, A and B. Initially, they don't get separated. As the components move together, they will get a separation. So the separation occurs. And now you can see as the distance migrated in the column increases, separation has increased. And now B is very clearly separated from A. And as you can see, the more time the material spends on the column, the component spends on the column, more the peak becomes broader. And the broader peak is not good for chromatography. Why it is so, we'll see that, and you will understand the concept of that. So now I have these two components getting separated under three different conditions. Now, looking at it, you can easily tell me which one is better. The first one is absolutely wrong because we are not getting any separation. Second one, we are getting separation, but the peaks are broad and it is taking more time because the x-axis is time. So time taken by the component as they elute is longer. And we have seen my juggler where we say speed of analysis is important. And if it takes more time, it is not a good analytical technique because I want to have the analysis time reduced. Now, if you see the third one, where it is a good separation, the peaks are sharp, and the time is reduced. So this is what is a good chromatography. So in case of a chromatography, the punchline is good separation in less time. So always remember that when you have to develop a method in chromatography, remember this catch line that you have to obtain a good separation in less time. Then only you are a good chromatographer. Okay, so everybody tries to reduce the time. If you reduce the time, time is money, first thing, and then the consumption of mobile phase for the analysis will decrease because the separation happens in less time. Each solvent cost a lot, especially HPLC grade solvent cost a lot. And that is why this needs to be understood that why time is an important factor. But remember that we cannot compromise on the separation. We want to have a good separation, but in less time. So every chromatographer works for this. Okay, so we have to understand some terms which are very important in chromatography. So if the component is put onto a column through the mobile phase, what is more important that the component has to spend some time on the column. Now here I am showing two peaks. One is the peak because of the mobile phase itself. So mobile phase goes from one end of the column, goes to the end of the column. And whatever time that takes is called as T0. The mobile phase also is going to take some time from beginning of the column to the end of the column. So that time is called as T0 time. The component which you have put has to remain onto the column for longer time, and it is taking time which is called as TR. So first term which we have to understand that there has to be a capacity of the column to take your analyte and keep it in your that column for some time. So column should have a capacity factor. Unless and until column has a capacity factor, you cannot achieve a separation. If column has no capacity to hold that analyte onto the column, what will happen? It will come the time of T0 itself. Sorry, I will just put my yeah. Can you see this? Yeah. Okay. So if the analyte has no capacity to be there on the column for longer time, it will come out here itself. So there is no point in having, there is no chance of a separation because the analyte is coming along with the mobile phase. So we don't want that. So column should retain an analyte for some time, and that needs to be found out. And for that, and that is called as capacity factor. We calculate very simply by knowing the retention time of the analyte minus Tm, that is retention time of mobile, divided by retention time of mobile phase. You can find out what is the capacity factor of the analyte. So for every analyte, there has to be a different capacity factor. If the capacity factors of both two analytes, suppose I put two analytes, if both the capacity factors are exactly same, what will happen? The second component will also come out at the same time. So it will just go within this them because both have same capacity factor. So I need to have a different capacity factor. So that, what does it mean? That between two components, the column is selective for one of them, so that one is retained more than the other. And that is why we come into another term, which is selectivity factor, and which is denoted by term alpha. So now here you can see these two components have different capacity factors because of which they are getting separated. The first one is coming little, so its capacity factor is less, K1 dash or whatever we call it as. There you can see that alpha is equal to K2 dash upon K1 dash, or yeah, K1 dash. So K2 dash, that is this, is having more retention time. So it is retained more. So for its the capacity factor is higher, and that is why alpha gives us a selectivity factor which tells us that this alpha has to be more than 1, because K2 has to be more than, or K2 dash has to be more than K1 dash, then only we can achieve a separation. So selectivity factor is very important. If there is no selectivity factor, you will not be able to get good separation. So these two factors are very, very important in chromatography. A capacity factor as well as selectivity factor. We come to one more factor, which is called as column efficiency factor or number of plates factor. Now these number of plates are very, very important. I'm not getting into the theory of this. There are two theories behind it. There is something called as plate theory. There is something called as rate theory. Calculation of number of plates, which is very easy. You can calculate number of plates on the basis of this formula. Now I will just, in simple language, I will just explain what is it. Number of plates can be said that the column has number of plates, which are called as theoretical plates. We cannot see them, but every column which we are trying to use has a number of plates inside. More the number of plates, the column is good. Less the number of plates, column is bad. Now what happens if number of plates are higher, you get this particular peak more sharper. If number of plates are less, you will get broad peaks. So what is the advantage? If the peaks are sharp, you can, in the same time, you can have many components getting separated, because within this width of the peak, I can definitely separate 2 or 3 more components. If the peak is broad, if peak is sharp, I can definitely get one peak here, second peak here, third peak here, and I will be able to separate 3 components in that width of the peak. So width of the peak is very important, and you can see from this formula that width is at the bottom of this. So if width is small, n will be large, and n has to be large. We calculated by this equation, which is very simple, because TR is the retention time of this component divided by width of the peak in the same unit or as time, and you can calculate number of plates of column. And this is always given by your instrument. The software will tell you what are the number of plates of your particular peak, and you can say if number of plates are good, your column is definitely better. Okay, so this is one number which is very important, and there is one which is called as resolution. So if we have seen some peaks where we do not get a good resolution. When we say good resolution, when the one peak comes down, goes to the baseline of the peak, and then you get another peak. Okay, so when you get such a kind of a resolution between two peaks, you can say the peaks are well resolved. And then you can calculate resolution factor by this formula, and resolution factor RS, which is given here, has to be more than 1.5. So if we have resolution factor more than 1.5, the peaks are well resolved. For this, resolution factor may be 1. For this, it is 0.75. So those peaks are not well resolved. And what is my punchline for chromatography? I should get good separation in less time. So I cannot compromise on separation. I don't want this kind of separation. I don't want this kind of separation. I have to get a separation like this. Okay, so I need to know what is retention factor, and I can calculate that again on the basis of retention time and the width of the peak. And it is very easy to calculate. Again, your instrument will be able to give you through the software all these values, and the resolution factor has to be more than 1.5. Whenever you develop any analytical method based on chromatography, they will always see what is the resolution factor. Okay, so resolution factor is a very important term. Okay, I'm just going through this four diagrams very quickly. Here you can see I'm talking about, so these chromatograms are same. There are three components getting separated. Here I'm talking about width of the peak. And as you can say, as the retention time increases, width of the peak becomes more. Okay, so because the component spends more time inside the column, it gets diffused because of the flow of the mobile phase as well as the interaction with the stationary phase. So it becomes more broader. The peak which comes earlier is more sharper. The next peak is little sharp, and this is little broad. So this width of the peaks are very important. If I can increase the column efficiency, I can even reduce the width of all these three peaks. So I can achieve a good separation in less time and with very sharp peaks. I will come to you why these sharp peaks are required. Now here I am talking about retention time of the peak. Now retention time of a peak is calculated on the basis of the response given by a peak at its maximum. So here the peak maxima is there. So whatever this peak maxima comes, it is the retention time of that peak. So retention time of A, retention time of B, retention of C. This is very important. This is the qualitative aspect of chromatography. Under given condition, you get retention time of the components, the phase velocity, column, temperature, whatever factors which are responsible for all of them are constant. Retention time of a particular component will be constant. So you can use that as a qualitative measure. So if you have a mixture in which suppose that component is there, and if you get a peak at this particular retention time, you can say this compound is present there. Okay, so retention time is very important, and it tells you about the qualitative analysis. There is another which we talked about resolution. So this X is a resolution between two consecutive peaks. Y is between these two consecutive peaks. And as I said, this resolution has to be more than 1.5 for all this. So it should be more than 1.5 here. It should be more than 1.5 here. And as you can see, as there is a baseline resolution here, the resolution has to be more than 1.5. So these tell us about resolution between peaks. And this is very important because this is a quantitative analysis measure. We call it as area under the curve. So the area of this peak is related to the concentration. So if I have a standard, I measure the area under the curve for a standard. So A, B, C, I measure the area under for all those. So these are vitamin A, vitamin B, vitamin C. I have vitamin A standard, I have vitamin B standard, I have vitamin C standard. I measure the standard known concentration, area of those peaks, and then I have a formulation of vitamin tablet, and then I inject that, and whatever area I get for that sample, I can relate those areas and find out the concentration of that vitamin tablet which I have, individual vitamins present in that. So this particular four diagrams which I have given here, those are very important as far as chromatography is concerned. I am now getting into instrumentation, and this is an example. Again, let me tell you about this is gas chromatograph. I am not going to talk about a GC because more biological scientists than GC. GC is only used for volatiles, and there are only 10% of compounds which are volatile. 90% compounds, organic compounds and biological compounds which are non-volatiles. Non-volatiles can be separated by LC. Only volatiles can be separated by GC. So there are 2 punch lines. If you want to separate something by GC, GC evaporate and separate. And if you want to separate something from by LC, LC will just ask you that if you can resolve, I can resolve. So there is a limitation for GC that it can only do 10% of the compounds. That is why we are not going to spend more time on that. So this is just for your information. This is the injection port where you can do the injection by using the syringe. This is the column. So the sample will get into the column. Column has to be kept at higher temperature because we are talking about volatiles. So the injection port which come in form of solution get evaporated, and that evaporated sample goes on to the column, gets separated, comes to the detector. There are various detectors here. I'm not going to, as I said, I'm not going to talk about that. And those detectors will give you a signal, and GC is used for all the volatile compounds. In biological samples, probably you can we can talk about the essential oils which are volatile. Then we can talk about the low molecular weight fatty acids. We can analyze by the GC. And then we'll see what are the components which are possible by GC. I have some nice that slide. So you can see these are the compounds which are having low volatility. These are the compounds which are having high volatility and high polarity. So here the polarity is less. Less polar compounds and more volatile compounds can be analyzed by GC. More polar compounds, and then they are non-volatile, or there is one more criteria: the compounds which have which can get degraded before their boiling point, they get decomposed before their boiling point. All such compounds can be analyzed by LC. So this is very thin line which can distinguish between LC and GC. So on one side we have GC, but though the number of rectangles which you are seeing here with the names, they appear to be more. The number of compounds which are volatile are only 10%. There are a lot of compounds which are non-volatile or get degraded before their boiling points, and these all compounds can be analyzed by LC, and that is why I'm going to concentrate more on LC. Okay, so HPLC to HPLC, I'm not going to spend more time on that. This is some funny way of pronouncing, or I mean the full form of HPLC. When Mikhail Sweat started till 1965, the instrument came into existence using only column chromatography, and it's in premature condition. I call it as highly premature liquid chromatography. Then people realized that if we want to have an instrument for chromatography, we have to reduce the particle size to get good separation. And then if the particle size is reduced, liquid may not be able to pass through, mobile phase may not be able to percolate through that. So we require to have a pressure on that. So they developed high pressure liquid chromatography. So 1965 instrument was not high performance liquid chromatography, it was high pressure liquid chromatography. Because of the initial breathing problems, it had a lot of different funny names. It was called as, I mean, I gave some names like that. So high pressure leaking chromatography, high prestige liquid chromatography. It was only sitting in the lab showing that we have a good HPLC. It was hardly performing liquid chromatography. But when people work on these problems, and with new columns, with new detectors, and with technology, it became high performance liquid chromatography. And today, with further more developments, it is called a high power liquid chromatography. Fine. So this is in short chromatography cartoon suite. But then what are the parts of chromatography: pump, injection system, column, detectors, and data system. Okay, so I'm not, so this is isocratic system. We'll quickly find out what is isocratic and what is gradient. Okay, so this is a gradient HPLC where you can have four mobile phases. Here there is only one mobile phase, and there are four mobile phases here. So this is called as quaternary gradient system. And there are two methods of gradient system. One is with three pumps and three mobile phases separately. Here only one pump, but four mobile phases are mixed in a, and then they are, there is slight difference between the way they are um, getting into the system, but rest of the things are constant. So this is the difference between isocratic and gradient. In isocratic, the composition of mobile phase, even if you have two different solvents mixed together, but the composition of mobile phase remains constant throughout the analysis time. So all the components are separated with the same composition of mobile phases. While here, the mobile phase composition changes during the analysis, and because of that, we can change the mobile phase composition. The advantage is that we can take out the analyte which is retained on the column for longer time. By changing the composition of mobile phase, we can take it out from the stationary phase, and then it can be pushed out of the system, and you can measure it much better way. I will just give you some example. Here there are two runs which are taken at two different mobile phases, but in isocratic. I'm not changing the composition of mobile phase, but look at this, where I change the composition of mobile phase, methanol and water, and now by changing the composition of mobile phase, all the components are getting separated in less time. Here the time taken is more, there is a good separation, but time taken is very high, peaks are very broad. Here time taken is less, but these peaks are not getting well separated. So our punchline of chromatography is lost in both the cases. Here time taken is large, here time taken is small, but there is no good separation. Here we are getting good separation in less time. So this is what is required, and that is why we require a gradient HPLC system. So this is, I'm not getting into this because I have time which is less. So this is, there are different pumps. So this is reciprocating pump. You cannot inject the sample by injection syringe into the system directly. So you require a different device which is called as a sample injector, and there is a loop behind it. So sample and connect this system to chromatography. This injection port is connected to chromatography, and in such a way that after filling the loop, the mobile phase will then pass through the loop and will take the sample from the loop to the column and then to the detector. By that means, because your mobile phase is at higher pressure, you cannot use direct syringe as you can use it in a gas chromatography. So you have a loop here. So this is the way the design is. Initially, the pump is pushing the mobile phase directly into the column. You are filling the loop in different ways. So you are putting the needle port and filling the loop, and then the excess is going out to the waste. Here you change the position of the valve in such a way that in the inject mode of the valve, now the mobile phase will go like this. It will go through the loop and then will go to the column and to the detector. And that is how you do the inject mode. You allow the sample to get into the system. So this is called as a Reodan valve, which is always a part of every HPLC system. Then we come to the column. As I said, column is the heart of the system, and you have different types of columns available. This is made up of stainless steel because it has to withstand very high pressure. So this is very hard and thick in diameter. The inner diameter of this column is about, normal column is about 4.6 millimeter deep column. And then this column is packed with the stationary phase. Inside there is a stationary phase, and the separation would occur onto the stationary phase. The column, the outside material is stainless steel. There are two methods of separation. One is called as normal phase and reverse phase. The normal phase, where the stationary phase is more polar and the mobile phase is non-polar, more non-polar, then it is called as normal phase chromatography. And reverse phase chromatography, when stationary phase is more non-polar and mobile phase is more polar, it is called as a river phase chromatography. So there are two modes of operation of liquid chromatography, and maximum time people use river phase chromatography. This is how the difference between normal phase and river phase. Now you can see a silica. There are a lot of polar hydroxyl groups on the silica. So this is polar stationary phase. So when you use silica as a column, it becomes a normal phase chromatography, because in case of normal phase chromatography, we have a polar stationary phase, and then we use a non-polar mobile phase like hexane or ether or something like that. So that will be a normal phase chromatography. Now, same surface of silica, we can make it non-polar by putting some bonding onto that. So this is called as octadecyl silane, which is bonded to the hydroxyl group. Now, because of this hydroxyl group, the surface of silica is polar. Now I'm making it non-polar by having this kind of a bonding. Now this is called as octyl silane column or C8 column. Instead of octyl, if I take octadecyl, then it becomes C18 column. So instead of the carbon, this ring, this chain of 8 carbons, it will be 18 carbons. So more the length polar, this is a non-polar compound. The alkanes are non-polar. So because of the chain of these alkanes, the surface becomes non-polar, and then this becomes a river phase chromatography. Phase chromatography, we have surface which is non-polar and the mobile phase which is polar. So here we can use methanol water as a mobile phase. Okay. There are several detectors in HPLC. We are not going to talk about each one of them because of the time, but I will show you some of the separations which are occurred on this detector, because these detectors are specific detectors. You know, visible detector can most of the, so UV detector is a very common detector in HPLC, but only of course the condition is that the compound should have chromophore. It should absorb either ultraviolet or visible radiation. So this is a separation of amino acids not directly absorbed, so they have been derivatized. And then I have done the separation of amino acids on a column. So this is by using a UV. Modification to UV, it is called as a PDA detector, photodiode array detector. The principle is same. We use same deuterium or tungsten lamp. Only the thing is that we get a spectra instantaneously because I'm using several detectors here, and there are 512 elements photodiode array. So for each individual wavelength, there is a detector. So when the grating would disperse the radiation, polychromatic radiation, individual wavelength will fall on these detectors, and you get a simultaneous spectra as well as chromatogram. So it will look like that. So this is a chromatogram, and on a chromatogram, at any moment, I can look at the spectra. So what you are seeing here, the black one, is the spectra of that compound. Now, if the compounds are different, you will get a different UV spectra. So you can see here, this compound has a UV spectra, the black one, different than this. So you can distinguish the compounds and can, to some extent, identify the compound. So this is the 3-dimension data which you can get because of the PDA. This is a fluorescence detector, and here I have done the same amino acid analysis, and fluorescence is a very sensitive detector. So same amino acid analysis I have carried out by using fluorescence sterilization, and you can compare the signal of fluorescence detector easier, and this is the same signal which we got by using a UV detector. So UV detector gave a very poor response, while fluorescence detector we gave a very high one because of its specificity and sensitivity. This is a electrochemical detector where I have separated catecholamines. Now catecholamines are biologically important, diagnostically important, because they are related to some kind of brain diseases. So analyzing these catecholamines is very important. And by using electrochemical detector, we can analyze catecholamine. Electrochemical detector works on a principle that any compound which can be oxidized or reduced can be analyzed. Like amines can be oxidized to nitrates, or nitrates can be reduced to amines. So both these type of compounds can be analyzed. Aldehydes can be converted to acids, and acids can be converted to aldehyde by using oxidation or reduction reactions. So such kind of reaction, any redox reactions, if they are happening to a compound, they can be monitored by using this electrochemical detector. This is a conductivity detector which is used with ion exchange chromatography. And here I've done separation of anions by using ion exchange chromatography using HPLC instrumentation, only column being a ion exchange column. This is anion exchange column. I've separated fluoride, chloride, nitride, bromide, etc. This is cation exchange column. So the same technique, I've used separation of sodium, ammonium, potassium, magnesium, calcium, etc. at ppm level. So this is ion exchange chromatography. This is a refractive, and there are many compounds which can be measured by UV visible, like sugars. They do not have any UV absorbance. Now they can be measured by refractive index detector, and you can see separation of various sugars by using the refractive index detectors. So in turn, you are looking at the applications and also the quality of the detector where it can be used. Well, we come quickly to the applications of LC. I will take little more time, at least 5 minutes more. Okay, so this is general application: drugs, biological and natural compounds, food analysis, environmental analysis, a lot of organic compounds, and also for clinical diagnosis. So these are some examples of that. So this is one, anti-inflammatories. Then we have basic drugs. Then we have uh, these are what, antihistamines, or what is written is not making me allowing to read that. Okay, this is metabolites of uh, yeah, benzodiazepines and its metabolites, antidepressants, benzodiazepines and metabolites, and this is OTC anti-allergic compounds. This is morphines and drugs. These are chiral compounds, so even you can separate optical isomers by chromatography. Of course, you require a chiral column, a different type of column. So I've just given you some example of application of chromatography. Only column needs to be changed. Rest of the instrument remains same. So we require different columns for chiral compounds, which are optically active compounds, D and L isomers. This is natural products, flavonoid analysis by HPLC. These are again oligomers, probably, I'm not very sure. These are sugars, fructose, glucose again. These are beer, from beer probably. These are beverage additives. This is protein mix. So again, biological application, bioactive peptides, so proteins and peptides. This is nucleosides. This is organophosphate, pesticides in food, which is a very important subject nowadays. You will see one major application of this when I talk a little bit about LC-MS. Then this is pesticides, organophosphate. This is organochlorine pesticides. Then this is polyaromatic hydrocarbon, PAH, which are pollutants, and they can be measured very easily by, you can see there are 17 compounds which are separated by HPLC. These are explosives, so RDX and TNT, and so good application for forensic application. So these are the compounds which can get separated. These are the, I think this is metabolites of particular drug. I'm not very sure. These are the diagnostic application. No, sorry, this is retardants, flame retardants. And these are all brominated compounds, hexabromocyclodecan, and this is tetrabromobisphenol A. So these are flame retardants. They are very useful in coating some substances where there is a possibility of catching fire. These are again, I think these are different compounds. These are polymers, I think polystyrene. Okay, I'm not able to see, something is coming, hiding my presentation here. These are polystyrene. So these are different molecular weights, 8.42. These are the molecular weights of those. 79K is 79.1K is kilodaltons, so many thousands. Okay, then how the HPLC looks like. Okay, so the current HPLC looks like this, and it is without the PC. So it has its own screen. you need not have a PC around the instrument. That is what people are now looking at, the instruments with always a PC around it. So this HPLC is without PC. It has a lot of advantages. You can have something like 20 HPLCs. It occupies very less space, and you have a computer somewhere else. And people can operate from that computer all these HPLCs. 20 HPLCs can be operated from somewhere else. And then not only that, you can take a control of this HLC from your Android. So if your mobile, you can have a control of this LC. So if you are at home and you want to look at some of the results which are being done, because you are running the system 24 hours, and you want to look at one sample which you have analyzed on the system, you can look at the results from your Android. And then if you want to run a particular sample which you have loaded there, and suddenly you want to have urgency of running that sample, you can stop the run and tell your instrument to take that sample first before all other samples. And that is how you can even do that kind of analysis. So you have all the controls of your instrument from your home, from your Android, and that is how the automation has come into the HPLC. So HPLC has become fully automatic because of that. Okay, so the HPLC looks like this. It has auto sampler, so you can load 384 samples and run all of them one after the other without anybody attending the machine. This is a fast LC. Now, the new LC which has come, which doesn't operate at 6,000 or 9,000 pounds per square inch, it operates as 18,000 pounds per PSI. Okay, so that's kind of a pressure, and it uses very small column. So it decreases runtime, the speed of analysis is high, it gives you higher sensitivity, it gives you much higher resolution, gives better quantification, and it reduces process time, and you have less solvent consumption. So the fast LC has come into the market, and they have a lot of advantage. Let us look at some of the chromatograms with normal LC and fast LC. Here, this LC has taken about 15 minutes for analysis. This is your normal LC, 1 ml per minute flow. Here the flow is high, but the column is very small, and the analysis is over in less than 2 minutes. So 15-minute analysis time has come down to 2 minutes, and you can look at the resolution. The resolution is still very good. So you are not compromising on separation, and you are reducing the time. That is what the punchline of LC. Have a good separation in less time. So that is here it is still separation are used as food additives, and you can see separation is over less than 1 minute, less than 0.5 minute. Okay, so this is all the 5 parameters are separated in less than some 30 seconds. That is the kind of speed we're talking about in case of today's HPLC. So development has taken place to that extent. This is one example where xanthine oxidase metabolites, which are run on normal LC, which took 12 minutes, and when it is done on fast LC, this is real example, and this is done in 4 minutes. So that is the advantage of current HPLCs now, which are fast LCs. And today, a lot of people use fast LCs in their labs. Okay, so that reduces runtime, that reduces method development time, everything comes down, and people are moving from the fast LCs even to micro LCs and nano LCs. So people are not talking about a 40 microliter per minute flow, not 1 ml per minute flow. People are talking about 200 nanoliter per minute flow. So with these kind of flows, 1 ml of mobile phase will last for 1 full day or even more than that. Okay, so you can run with 1 ml of a mobile phase, you can run a machine for more than few hours. In all the 3 shifts, probably you can run the machine. Okay, so that's the advantage of people are going from micro LCs to nano LCs. Okay, now LC is coming on chip. This is the chip. It is a capillary column which is used for separation, and it is a very simple technique which can be connected to mass spectrometry also, and you can have a LCMS by using this kind of a chip technology. It is CHIP chip, it is not the other way chip. Okay. the talk on LC will never get completed unless I talk a little bit about mass spectrometry as a detector. So chromatography alone with all other detectors gives you only one dimension, that is retention time. And on the basis of retention time, you say that this compound may be present. But when you add mass spectrometer, it also gives you molecular weight. So now you have two dimensions. One is your retention time, which is very specific to your compound. But then the same retention time can elude. But when you get a molecular weight information, you are sure that this could be your compound. But in addition to that, fragmented, you get what we call spectra. And if the mass spectra also matches that of a standard with that of your compound, with the molecular weight information also matching, you have three, and you see definitely this compound is present. So MSMS adds, or LCMS or LCMSMS adds all the bias. It gives you much higher sensitivity. It gives you a lot of selectivity. It gives you much better separation. LC does separation and MS does additional separation, and MSMS does still wonderful separation. It gives you structural information and it has a very, very high speed. Let us look at one last example. This is how LCMSMS looks like. And you have this wonderful example which I have chosen. I have separated 836 pesticides in a food in less than 15 minutes by using LC-MSMS. Now this is impossible by LC alone. Only it is also impossible by LC-MS alone. But when I have a combination of LC-MSMS, then I can achieve this kind of a separation. 836 pesticides are separated on LC connected to MSMS system in less than 15 minutes. And that's where the people are moving now. People are moving from LC to LCMS to LCMSMS. And that is the development which is happening in the market. Okay. So conclusion in short, I'm not going to read everything. I'm just going to explain you what I've written there, that the development which are taking place in the analytical instruments makes scientists or get to make scientists get a lot of data, and a lot of good research happens because of development in the instrumentation. Another thing is scientists face a lot of challenges, and then instrument people meet them, discuss with them, try to understand their challenges and come out with a solution for them. And both these things work together. So instrument people build good instruments for the scientists, and the challenges coming from the scientists help instrument people to develop new instruments. Okay, and this goes hand in hand, and this will continue forever. And that is how the instrumentation and especially HPLC has progressed. Thank you very much. And I would like to conclude by saying same thing about, I started with chromatography. I want to also talk about chromatography in this way, that the punchline which I said, good separation, less time. This is applicable to corona also. If you have a good separation, you follow social distancing, we can drive corona out of this much early in less time. So good separation and less time both are also related to corona. You follow that and be safe and enjoy these holidays which you are getting in learning something more from the kind of web seminars and these kind of seminars which are conducted by your staff, your teachers. I congratulate them for these kind of activities which they have started, and thank you very much to all of you. Let's stop, and if you have any questions, I will take.
Yes, sir. We'll start with the question and answer sessions. Pratibha, could you please start that? I also request you to take a few questions from our live YouTube streaming that's happening. There are questions being posted there as well. Over to you, Pratibha.
So there's a question that how to calculate retention time.
How to calculate?
Retention time.
Okay. Now, the retention time can be easily calculated by, if you have a stopwatch in your hand, when you put your sample inside. So when it is in HPLC, you turn the valve, or you have a sample injection system. If it is auto sampler, when you push the button on auto sampler and when the sample gets injected, start point, that is the start time. And from that till the peak maxima comes, so you start getting your peak out from the detector. And when you record your peak maxima, what time it takes from the start to get that peak maxima is retention time. Now, earlier days when I started using chromatography way back in 1971, when I started doing my PhD, we had no data system like what you have today. So I had to really look at the time with the stopwatch. But now you don't have to, because instrument calculates the retention time for you. How it does it? It is easy to understand. When the peak starts and when the peak goes beyond some threshold, because there could be noise. So noise is that you have to set some threshold value, otherwise it will start giving retention time for every small noise also. Threshold it will consider as a peak. And what it does, it measures the slope of that. When the slope is positive, it will record that the peak is the peak negative, it notes the time at that point. And that is how the retention time is calculated using a software, which goes on looking at the time. And when the negative slope starts, it puts that time as a retention time for your peak. From the peak, from the start of your sample injection to the time it sees its maximum. Okay, that is called as retention time. Your instrument does it for you now. You don't have to really measure it. If you have the old system, you can measure it by using the stop. Yeah. Any other question?
Yes, sir. How do you determine which detector is to be used in HPLC?
Yeah. Okay. Now for that, you should know something about your analyte of interest. If the analyte has a chromophore, that means it absorbs in UV range, UV or visible range, wherever it is, you can use a UV visible detector. If again, if you want to have a detection at a very low level, and if your compound is amine, and you find that some of these amines are not possible to be measured by UV detector because of no this is aromatic. So in that case, you have to use the detector which I mentioned about, that is electrochemical. So depending upon the type of compounds analyzed, you have to choose a detector. Okay. Yeah. Question?
Yeah. Okay, sir. Sir, can we have a combination of 2 or 3 detectors in HPLC?
Yes,
There's one
that's a good
question.
question. Especially in HPLC, most of the detectors are non-destructive. So UV is a non-destructive detector, refractive index is a non-destructive detector, electrochemical is a non-destructive. So many detectors being non-destructive detectors, you can have them in series. You can, if one component doesn't get detected in one detector, it may get detected, or you can get both detectors if it gets detected in both the detectors. Okay, so you can have a good combination of detectors if you want. If you have them, you can put them in series also. So that's a possibility in case of HPLC. In case of GC, most of the detectors are destructive detectors. They are flame detectors. So sample gets decomposed in the flame. So you cannot have those detectors in. Any other?
Sir, yes, sir. There are many questions actually. I'll take a few.
Okay, fine.
Yeah,
I
yes,
can
sir.
answer.
Yes, sir. There are few I'll take up. Why do we get
Yeah.
unstable or negative peaks sometime during HPLC? There's a question.
Yeah. Okay. Now, yeah. Negative peaks generally come when the detector response is different than the other components. If the detector response is negative compared to other components, you get a negative peak, one of the peak negative compared to other peaks. It can happen in refractive index detector, very common, because in case of refractive index, the refractive index of mobile phase and the refractive index of both are compared. If the refractive index of your sample is more than the refractive index of the mobile phase, you will get positive peak. But if there are 3 positive peaks, and if one component has a refractive index less than the mobile phase, you will get a negative peak. So this can happen sometimes. And the disturbance or distorted peaks come if the column is not very stable. Like if column gets contaminated, you can get disturbed peaks or distorted peaks. So the reason could be using several injections, lot of impurities which are not noticeable otherwise get accumulated on the column, and column can become bad after some time.
Okay. Sir, is there a specific method that you would like to suggest for preparing HPA samples for HPLC for effective separation?
Yeah, sorry, can you repeat it?
Yes, sir. Is there a specific method that one should follow for preparing sample for HPLC separation?
Yeah, okay. Now HPLC is a technique where you have to have a sample which is soluble in some solvent. Okay, so that is I said, if you can dissolve, it can dissolve. So sample should dissolve in some solvent. Now, if there are some suspended particles in that, or there is something which doesn't get dissolved, then you have to filter it through some specific filter, 2 micron or 2 filter, and then use that. Because if you can envisage that the entire sample may not be in solvent, not be in solvent, there could be some particles in that, and those particles can spoil your column. So that is why when you have to do a simple sample preparation, it is always better to filter your sample through filter and then use them. Then your column life will be longer. And whatever solvent the sample is soluble in, you have to choose that solvent. And it is always better to choose a solvent which is your mobile phase. And if you have sample, you have to use a polar mobile phase, dissolves. So on the basis of that, you have to select a solvent. And it is always better to have a dissolution of your sample in the mobile phase itself. If it happens, well and good. Otherwise, you have to choose a solvent which is polar or non-polar, depending upon whether you are using reverse phase chromatography or normal phase chromatography. Yeah. So filtration is must. Okay, you have to filter your sample and choose a proper one for dissolution of sample.
Okay, sir. Sir, how to decide solvent ratio?
Yeah, how to decide
Solvent ratio.
solvent ratio. Okay, the
Yes,
mobile
sir.
phase, not mobile
Yes.
phase ratios. Now, this is a method development part. So you have to start with, generally when we use reverse phase chromatography, we start with say 50% methanol, 50% acetonitrile, or 50% methanol, thing like that. And then how, what kind of a separation you get. Generally, when you are carrying out some kind of analysis, you first try to do some literature survey. Try to find out if anybody has done similar analysis. Try to get the information from the literature. If no information is available, you can start with simple things first. You use this kind of a combination. Start with isocratic, don't jump into gradient. Then change the composition of your mobile phase. If you find there is some separation happening, how the separation can be improved further by changing the composition of mobile phase. Then you see there are to add organic. That means instead of mobile phase being methanol water, if I can add acid, what happens? Because it becomes more non-polar to water. So it will take out which is adsorbed on that non-polar surface of a reverse phase chromatography. It will take it out and you can get a better separation. So it all depends on start with simple things first and then get into little complicated and then try to get into a gradient run. So it is a very tedious process, method development for unknown. If it is a method available in the literature, then it becomes easy for you to use that method and then slightly modify it or tune it for your analysis. But I will always recommend to get into the literature and try to find out information from the literature before you try to develop something by your own. Yeah. Yes, any other question?
Yeah, sir, there is one
Yeah,
question in the YouTube channel. What is the minimum critical concentration?
Yeah, there are two
yeah.
terms that are very important in analytical chemistry. One is called as limit of detection and limit of quantitation. Now, for that, we have some specific ratios. if limit of detection, the signal to noise ratio has to be 3:1 or more than 3:1. So when we have a signal to noise ratio 3:1, we can say we can detect the compound. This is the minimum compound which we can detect, signal to noise ratio 3:1. If it is less than that, we are not sure whether that compound is present or not. Now, if I want to quantitate it, then limit of quantitation, signal to noise ratio has to be 10:1. So when I get signal to noise ratio 10:1 or more, I can do a quantitation and I can say this is the minimum amount which I can quantitate. Okay, so you have to determine these ratios with respect to whatever detector you are using, whatever method you are using. So you have to calculate LOD and LOQ values. And on the basis of that, you can decide how low you can detect, how low you can quantitate. Okay, am I clear?
Yes, sir. Yes, sir.
Yeah.
So one question, if it is a
Yeah.
novel compound and if we don't have any reference, then what should one do?
Sorry.
If it is a novel compound that they have
Huh.
isolated and there
Yeah.
is no reference compound, then what
Yeah.
should one do in that
No
case?
reference at all available.
That is what the
No
question is, that there are no
standard available.
yeah,
No standard available or no
no
reference
standard
available in the
available.
literature. No standard
Yeah,
available
no
or no
standard
reference
available.
available.
Sir, it is written as no
Yeah, if there is no
reference, but I
standard available,
assume
you cannot do
the
quantitation.
person means is
First of
standard.
all, no standard available, you cannot do quantitation. For quantitation, you should have a standard. Okay, that is one thing. And if there is no reference available for developing a method, you at least know what is that compound and what is its solubility, in which solvent it is soluble. So if it is soluble in polar solvent, the compound has to be polar. Then you can use a reverse phase chromatography. If it is soluble in non-polar solvent like hexane, you know it is more of a non-polar nature compound. So you have to use a normal phase chromatography. So that will first decide which chromatography technique you have to use. And then when you start working on that, when you start knowing about your compound more, whether it has a chromophore or not, whether it absorbs in UV or not, so which detector has to be used. So you have to go step by step, knowing more about your unknown compound, and then try to develop a method on the basis of that. So the first important thing is its solubility. So in which solvent it is soluble will tell you what is the nature of that compound. Okay. And that helps develop a method further. And for quantitation, try to have
Yeah. So there's one question which is relevant in today's era. It is asked that whether chromatography can help to detect
Sorry.
viruses.
No, sorry, I'm not.
Whether chromatography can help to detect virus.
Virus?
Yes. Can it be used?
No, as on today, it is not possible to be used directly. There is some literature which I've recently seen about coronavirus, especially by using a TLC. They have analyzed something. I have not gone through the entire article, which I've just seen the heading of that. So they have tried to do some analysis by using a TLC plate. Okay, so the company who is making this HPTLC very popular in India and Chrome, they have got some literature on that. I have not gone through it, but if I get a chance, I'll have a look at it. So there is a possibility to some extent, but it is not that possible. It is by MALDI-TOF you can get some information about the virus. Okay, that's a mass analyzer. With the MALDI-TOF, you can directly analyze viruses. Okay. But chromatography, I have not seen. HPLC, I have not seen. But TLC plate, I have seen some article coming from Chrome where they talk about TLC can be used for coronavirus analysis. Yeah.
So there's this one
Pratibha?
question for last one.
I think yes, one last question.
Yeah. One last question I'm taking for separation
no
of flavonoids. Yes, for separation of flavonoid. Yeah, sir. GCMS or LCMS? What do you suggest?
No, GCMS is very difficult because flavonoids are not volatile. Normal flavonoids are not volatile. They are highly polar compounds. Their solubility is in methanol. Okay, they are not soluble in hexane or those kind of solvents. So flavonoids being a polar compounds, they are better analyzed by LC, not by GC.
Okay, sir.
I have analyzed a lot of flavonoids for my research students. We have only used LC for that. We have never tried GC. It is not possible to be done by GC.
Okay. So
Unless
there are
you
many,
derivatize them and then do it.
sir, there are many questions, but we are stopping over here other because there is endless list of questions that we have in our.
You have time restriction.
Uh,
If you can, if quickly you can go through, if it is not a repeat question, and if you find it is good question, you can ask me.
Yeah, go ahead, Pratibha.
If you want to
Yeah.
restrict to some number of questions, you can do that. But otherwise, I have no problems. Or otherwise, they can write to me also if they have questions, or you can compile those questions and send it to me, and I
I
can
think
answer on mail.
I think sir will do
I can
that.
take, because I
Huh.
think still there are a lot of people on the, they're still listening, or some of them have quit. So
They are there still, sir. 400 of people are still there.
yeah, okay, then we can, I can answer some of the questions if there are some important questions according to you. You
Sir, yeah, sir. I'll just check.
can read them and decide whether this question needs to be answered properly.
One question where supercritical fluids can be used in chromatography.
Okay, okay. I did not touch that. There is one more mobile phase which I did not touch, because then it becomes, there is supercritical fluid which can be used as a mobile phase, and CO2 is the best supercritical fluid, and that technique is also quite popular. And supercritical fluid chromatography by itself is a subject, and that itself can take few hours if somebody needs to talk on that. It is a very important technique, and supercritical fluid also can be used for as a good technique, and it has major application in chiral chromatography. So supercritical fluid chromatography has good application in chiral chromatography or chiral compounds, and of course it has a lot of other applications also. Uh, but only the thing is that when it was developed, it was thought that it would replace HPLC and JC, but it has not become that popular for the reason that the supercritical CO2 is only semi-polar or more towards non-polar kind of a mobile phase. It is semi-polar, not very highly polar compound. So there is a restriction of using supercritical fluid CO2 as a fluid in chromatography, because it can only take few compounds for separation which are similar to the nature of supercritical fluid. And then if you want to make the supercritical fluid CO2 more polar, you have to add methanol to it. And by adding methanol, the supercritical property of that fluid itself changes, and you have to compromise somewhere else. So because of that, supercritical fluid has not become very popular as a technique. But yes, it's a very good technique for some applications. And SFC is a very useful technique.
Sir, there is another question. In case of new HPLC which works at very higher pressure, are there any new specially developed IC columns to take the higher pressure and avoid the back pressure that is generated?
No, when you have a high pressure, there would be definitely some back pressure generated. But then you don't use normal length column, which is 25 centimeter. Use very short columns, which are 3 centimeter length. And with those columns, and with the particle size getting reduced to sub 2 microns, you will have back pressure, which is to the tune of something like 18,000 pounds per square inch, 18,000 psi. And normal those HPLCs, fast LCs operate at 19,000 psi maximum pressure. So there will be a back pressure generated, but then all the precautions are taken, so there is no leak, and you get much faster separation when you use these kind of fast LCs, because the column length is very short. It is only 3 centimeter column length, or even less than that sometimes. Okay, so it has no problems. It is used in industry, and all major method development labs, they have fast LCs now. And even with MS, they use fast LCs, because MS itself is fast, and then with your fast LCs, the whole technique becomes very fast.
Yes, sir. One more question. can HPLC be used in food industry for quality control?
Food industry, yeah, it can be used. There are a lot of things that are possible to be. One thing is to find out the aroma contents in food. It can be used for pesticide residue contents in food. It can be used for vitamin analysis in food. So depending upon the type of food which you want to or you're talking about, you can use HPLC for all different types of analysis in food industry. Okay, so it has several applications depending upon the kind of food we're talking about. And current application is with respect to food safety, and where pesticide residue analysis has become very important. Antibiotics in food, like especially fish and meat, has become very important. It has become the elements like arsenic, selenium, mercury. Those analyses have become very important. So food analysis with respect to toxicity or toxic compounds and toxic elements, that has become very critical, as well as the quality of food with respect to proteins, with respect to vitamins, and with respect to aroma. All that is also equally important. So food industry, it is used quite extensively.
Okay, sir, I think that's all that we could see the questions in the chat box.
Yeah, okay.
If there are any more, sir, we will compile and let you
Yeah,
know.
you compile and send it by mail to me, and I will send the answers to all. So thank you very much for inviting me, and hope
Sir,
students liked it.
yes, sir. I would now, Setal ma'am, you want to say something?
Yes, sir. I think the students have just loved it both here on Zoom as well as on the YouTube. They're thanking you for such a informative and enriching session. Pratibha, please propose the vote of thanks.
Yeah.
Thank you. Thank you so much.
Yes, sir.
Yeah, see you sometime again in person now. We have met like this, but let us see we can meet in person sometime. Thank you
Yes,
so much.
Sir, could you please wait for 2 minutes?
Yeah, okay.
Yeah. It's my privilege to propose the formal vote of thanks for today's event. On behalf of KC College Microbiology and Biotech Department, I would like to thank Dr. Ajit Datar for taking us on such an enchanting journey for understanding chromatography and its application. Sir, your talk was very enlightening for all of us. There are many comments coming up thanking you for the same. You beautifully guided us from the very definition of chromatography to the new generation LC, LC on chip, LCMS. So the journey was indeed an enchanting one. As you said in your lecture that a good chromatographer can carry out good separation in less time. Similarly, sir, you have conveyed so much to us in such a short time that we are truly feeling very privileged and blessed for the same. We are very grateful to you, sir, for taking time out and addressing the gathering. We would also like to thank our principal, Dr. Hemlata Bagla, for always motivating us to move along with the times and guiding us to use the technology and keep moving ahead. I would also like to thank Dr. Sagarika Damle, our star status coordinator, for always supporting and encouraging us. No event is successful without its participants. So we would like to extend a very, very warm thank you to all the participants for giving such a positive response and attending the session. The lockdown may be stopping us from having physical classes, but we at KC believe that learning should not stop. With this intention, we have been conducting such online sessions and shall continue to do so. Today we were live on YouTube too. We request you to, in case if you still have some uncleared questions or doubts, go back to the YouTube channel, do watch the video, and you can comment and we shall forward the questions to Datar sir. We are also having a session for students on 15th May, which is titled Know Thy Intelligence. I'm sure it would be an interesting one and request all the students to register and attend the same. Once again, sir, on behalf of the College and Department of Micro and Biotech, I extend a very, very, very big thank you to you for coming us in.
My pleasure again.
Thank you. Thank you, one and all.
Thank you so much, and see you again sometime.
Yes,
bye,
sir.
Bye.
Thank you so much. Bye, sir.
Yes, bye. Yeah. Thank you. Can I?
Yes, sir. Yes, sir. Yes,
Sir,
sir.
you can leave, sir.
Thank you.
I request all the participants to fill up the feedback form. Certificates will be issued only if we receive the feedback forms, and the link would be closed within an hour. So please do that as soon
So
as
I
possible.
go out. Okay. Thank you.
Yes, sir. Thank you
once
so
again.
much.
Okay. Bye bye.
Thank you. Thank you. We request all the participants to fill the feedback form in an hour, because after that the link would be closed. So for certificate issuing, that is very essential.
We'll issue the certificates within the next 10 working days. You can also check your mails for the feedback link.